right? Today's problem is going to be reordered linked list. Basically, we're going to be given a linked list like this. Just imagine there's arrows in between them. And then we want to reorder the nodes of the linked list to become like this. So there's kind of a pattern here. The first node is 0. The second node is the n-1th node. Then it's the first node and then the n-2th node, so on and so forth, right? Practically speaking, this is number 1, this is number 2, number 3, 4, 5, 6, 7. And we want to reorder it in place, obviously. So we get this result. So let's get to it. So a problem with this is that the list only goes one way, right? So we want this thing to point here, but we don't have a reference here. If I were to send a pointer that traverses each element, even should that pointer reach the end here, and this is my head, sure, I can say hit.next is equal to pointer, right? I could say that. Then we'd sever this, and then we move this here. And then, well, let's say I kept track of a hit_next and move my hit next here. Sure, we can do that for the hit, but we can't really do that for this, right? Because the arrow is going the wrong way. So if we had the arrows going this way instead, then we would be able to do this, right? We would be able to have a pointer next. Then we can sever this, point this to 1, move the pointer here, and so on, right? This would work. So a potential solution that I'm looking at is to implement a reverse linked list. We have to reverse a part of this linked list somehow to be able to do what we want. And should we reverse it, like how many nodes do we have to reverse, you know? Because this is going to point to this, which is going to point to this, this, and this one should be pointing to a none, right? And if you kind of notice here, we are kind of splitting the array to 2, where everything on the left here is pointing to something on the right, right? And everything on the right half is pointing to something on the left. So we have to partition this thing into 2. We have to split our original input into 2 halves. One half will be pointing to the right, and of course this is going to be the end of the sublist, so this is going to be pointing to none, and the right half, which is reversed, and this is also pointing to none. And once we have this, then this is going to be our ideal state, and we can just do our merging, and it'll be really easy. So to sum it up, we have 3 tasks. First one, find the middle point. Second task, reverse the second half. And then third, merge the 2 lists. And that's it. So let's go and make this work. Okay, so finding the middle point. There's actually a trick. If you remember the fast and slow pointers algorithm, this first introduction of the fast and slow pointers algorithm is in the cycle detection problem. I'll have that in the description as well. But basically, you had a pointer called fast and a pointer called slow, and fast is going to move at twice the speed of slow. Slow is going to move 1 unit at a time. Fast is going to move 2. And then this is going to help us detect a cycle. But that's not its only use. So the fast and slow pointer can actually find the midpoint of a linked list. As you can see here, I'm just incrementing fast and slow. And then on this iteration, fast would reach the end of the list and slow would reach here. So we know that we've reached the end of the list because fast.next is none, right? We can't increment fast anymore. We've reached the end. This is as far as fast can go. And if you notice here, slow actually ended up in our middle node. And of course, this is an odd numbered list. So when we split the array, we're going to have 4 elements here and 3 elements here, right? But still, basically we've reached the middle array. And let me show you what happens in an even scenario. So let's roll back 1 iteration. Slow would be here, fast would be here. So in a even length list, we wouldn't have this. Our fast would move 2 units to the right. It'll end up here. So, you know, clearly this is going to be the end, right? This is going to be the end of the list. And then slow is going to move 1 unit. Although this is the middle, it looks like our slow pointer is pointing to the middle right element, right? In an even array. But I think conventionally, when we do problems and we want to split the array to 2 for binary search and stuff like that, we would prefer the middle left element out of convention. So because of that, we have to modify our code a little bit. So initially, when we started with slow here and fast here. And this worked fine for a odd numbered array, right? But we should offset fast by 1 so that the array will be split at the middle left element in the event that the list is even lengthed. And there you go. This does work for that. And just to show you as well, for the odd case, if I were to start like this, so the odd case, I'm going to add our 6 back in. Fast would move 2 units. Slow moves 1 unit. Fast moves 2 units. Slow moves 1 unit. And then now fast is going to move 2 units. It's going to end up at none. and slow will end up here. And see, it still ends up in the middle. So while we're traversing, we're obviously going to use some kind of while loop, right? So let's just write some code. So initially slow is going to be our head, which is this thing. It doesn't move right now. And then fast is going to be head.next, right? And it's okay, we're allowed to do this because there's a constraint in the problem that the list is at least one element long. And then next we want to write our while loop here. And this is the case where fast is none. So we want to keep going while fast is something and while fast.next is something. So fast.next being none would be like if it was here and we didn't have an element here. This would be like the even case, right? Odd case, it would be like this. And all we're doing is incrementing fast twice and slow once. And then when this loop ends, slow should be our middle element. So what do we want to do once we're at the middle element? Well, we know that our goal is to eventually have two different lists, and we're going to be reversing the second list and then we'll merge them together, right? So let's go ahead and split this list. So we know that if we want to reverse this list, then we need a pointer here, right? So I'm going to call that pointer head2. Head2 is going to be equal to slow.next. Bang, we got head2 over here. And then I want two separate lists, so it'll be easier to merge later. So I'm going to sever this thing. I'm going to say slow.next equals to none, right? Now slow.next is pointing to nothing. And just like that, we have two completely separate lists. And this is the code for finding the center. All right. Next thing we want to do is reverse this list. And reversing the list, this is a problem that we've solved before. The link to that will be in the description. I'm not really going to write the code for this. This is just box standard reverse linked list. So at the end of it, our structure will be like this. And then all we have to do is merge these two nodes. We're going to have a next one and a next two. Sorry, maybe I'll just call this next. So the general idea is that each loop, we want our head to point to head2, increment our head to next, and our next to head.next. And head2 will have that point to head, which severs this link, and we got to increment these two. So if I were to code it up, it's some kind of while loop. We have not determined the exit condition yet. And I'm going to define next and next to head.next and head2.next, right? Now we change the pointers, have this point to head2, then we move head to next, move next to next.next, and then we do the same thing for head2. And then we go round and round. That was one loop. Let's repeat this again. Head moves, next moves, head2 points to head. So next 2 is now none, and head2 is moved here. And then the third loop, this goes here. Now both next and next 2 are pointing to none. And then head2 is going to go here and we increment that. Oh, I made a mistake in the code. We shouldn't have this line because next and next 2 are incremented every single time this loop runs. In this very first line here, we have 0, 6, 1, 5, 2, 4, 3. And that's all good. So here, because, well, the left half is bigger than the right half, and then we also move both of the heads each iteration. Of course, head2 ended up becoming none before head1. And in the even case, let's say we didn't have 3 and it was just 2. Make this point here, head would be none, and then we make head2 point to nothing because head is already none at this point. So it'll just be like this, right? Same thing, 0, 6, 1, 5, 2, 4, and that's the end. And now both of them are none, right? Both head and head2 are none. And that's because they're both the same length. So they both ended up going to none in the same iteration. So because of the way we split our list, where we are more biased to having more elements on the left than on the right, head is always going to be greater or equal to head2, depending if it's odd or even. So in our exit condition, we want to stop whenever head2 is none, right? So we keep going so long as head2 has an element. So when head2 is finished, then it can only mean that head1 either none, which means it's an even case, or head1 has the final element, which is already pointing to none. So that's also not a problem. And this is going to be our code. Let's just copy paste it to the editor. So this is going to be the code to find the center of the list. And then we're going to need another chunk of code to reverse the second half of the list. And once we have that, we simply merge the two lists. And this would be the code to merge the two lists. Let's give it a run. And there you go. And that's our result. The time complexity of this is, well, for finding the center of the list, the fast pointer is going to iterate through every single node in the list. So this is pretty much O of n. And then reversing the linked list is also a linear operation, but it's only going to be for half the array. So n divided by 2, but you know, in big O notation, we don't really care about this. Merging the two lists, well, we're changing the lengths of each node one at a time. So this is also a linear operation. So all in all, our time complexity is linear, O of n. And as for space complexity, we are not using any extra storage. It's O of 1. We only have pointers. And that's about it. This problem references a lot to like the previous easy problems that we did for linked list. But I think it's a really good exercise to put, everything that we've learned into practice together, but with a little bit of twist. Okay, bye.